tell you about the synthesis of ketones. Now, there are several ways of making ketones, and one of the ways is to carry out an oxidation using ozone. If you have a double bond and you treat it first with ozone and then with a reducing agent, such as dimethyl sulfide, that's one of the reducing agents that are used. There are several, but this is a convenient one, although it is rather smelly. You will get two carbonyl compounds. Now, if any of these groups are R prime or R double prime or R triple prime, if any of those groups are carbon pieces, methyl, propyl, cyclohexyl, all sorts of stuff like that, then clearly you have carbon here and here if both of these are carbon. And so you'll get a ketone. And if these are also carbon, likewise you'll get a ketone. But if only this one and this one is carbon, and this is hydrogen and that's carbon, you'll get a ketone and an aldehyde. So if at one end of the double bond you have H, that end will give you an aldehyde. If at the other end you've got just carbon pieces, then you'll get a ketone. So that is one way of making ketones, simply ozonolysis of a double bond and reductive workup, as it's called. The other way of making a ketone is a method that you used, and right at the end of the last lecture I gave you this as an example. I just put up, I'm going to use this circle to represent the 6 delocalized electrons. The reason why I'm going to use a circle, of course, is that it was introduced into chemistry by a very famous Englishman, Sir Robert Robinson. And it means 6 electrons delocalized over the perimeter of the structure. If you take a compound like this and you treat it with an acid chloride in the presence of a Lewis acid, which is usually aluminium trichloride, you get a ketone. And I remember telling you that very often that procedure was combined with the use of the Clemenson reduction in order to remove the oxygen from the carbonyl and replace it by 2 hydrogens, so that the net result is that you get what you would get from an ideal Friedel-Crafts calculation. But you need to remember that an ideal Friedel-Crafts calculation is a very rare occurrence, because once an alkyl group becomes attached to a benzene ring, the benzene ring is more reactive, and so you tend to get polyalkylation, more than one alkyl group becoming attached to the benzene ring. And the way around this is to use the Friedel-Crafts acylation followed by Clemenson reduction. Of course, that's 2 steps, that's the price you pay, but the advantage that you gain is that the product is pure. So those are 2 ways of making ketones. There's another way of making ketones. You can make them from a class of compounds called nitriles. If, for example, you take a nitrile, such as, well, I'll draw up first of all the generic example. This is a nitrile. It's got C triple bond N and the carbons joined to some other carbon piece. That R group could be methyl, ethyl, propyl, cyclohexyl, benzene ring, substituted benzene ring, whatever you like. As long as it's a carbon piece, that is a nitrile. And if you treat a nitrile with a Grignard reagent, which I will write in this way, what happens is that the Grignard reagent attacks the carbon of the nitrile in the way that I've drawn. So that is exactly the same way in which, at least formally speaking, exactly the same way in which a Grignard reagent would attack a carbonyl group. It attacks the carbon, and the reason why it attacks the carbon is that the bond is polarized such that there's a slight deficiency of electron density on the carbon of the nitrile and a slight build-up of electron density on the nitrogen of the nitrile. So that's why it's the carbon of the nitrile that is attacked. And now, if you treat this material with dilute acid, what happens is that the C double bond N is replaced by C double bond O. And the way that that happens is presumably that the initial species is protonated on nitrogen, and then it's protonated on nitrogen again, and then water comes in, and then there is a protonation of the nitrogen once more, and a loss of proton from the oxygen, and the lone pair then expels ammonia to give you a protonated form of the carbonyl compound, which then loses the proton from the oxygen. So that is how that happens. And if you want a specific example, I'll give you a moment to catch up. Supposing I take this nitrile and I treat it with this Grignard reagent. And then, well, let me write down what I get first of all. Finally, on treatment with dilute acid, I would end up with that compound. you a more difficult example. Instead of telling you we take a certain nitrile, we take a certain Grignard reagent, this is what we get, then we hydrolyze and get the ketone. Instead of telling you that, let me put a different problem in front of you. The problem is, I want to make this compound. I need it for some purpose. How can I make it? Well, I notice that it is a ketone. Do I know any ways of making ketones? Yes, sure I do. I could oxidize an alcohol, or I could use ozonolysis chemistry. In other words, where I have a ketone, I need a carbon-carbon double bond. But then I've got another problem. How the heck do you make a compound with a double bond down here? Or I could use Grignard chemistry. Now, for Grignard chemistry, I could take this Grignard reagent and add it to an aldehyde. I'd get an alcohol here which I'd oxidize. Or I could use this Grignard reagent, add it to benzaldehyde, and then get an alcohol and oxidize it. Or I could use nitrile plus Grignard chemistry. So if I want to do that, there are two possible ways that I could do it. I could start with that nitrile plus this Grignard reagent, or I could start with that nitrile and this Grignard reagent. So which one I start with can depend on all sorts of factors. One of them would be if I went down to the chemical storeroom and found out that they didn't have both of those nitriles, but I wanted to make the compound. They had only, say, this nitrile, I'd have to use this route. But if they had only that nitrile, I'd have to use this route. So those are the sorts of things that go through one's mind when you have to make a particular compound. And you can see that even with a pretty simple substance like this is actually trivially simple for a professional, there are a number of ways you can do it. So you've got to know a fair amount to be able to decide which is the best way for you. And if you have all of these chemicals, then there's another factor. You have to look in the literature and see which one gives the highest yield. Or if, this isn't the case here, if the compound was new, so you couldn't find in the literature that somebody else had made it, so you couldn't judge which method gives the highest yield, you then have to do some literature searching to find out, in general, which types of reaction gave better yields. Was it aromatic Grignard plus aliphatic nitrile, or was it aliphatic nitrile plus aromatic Grignard plus aromatic nitrile? And then you could make some judgment. So it's not easy. It's not easy. Now, in order to make sure that you understand all this, over the long weekend, you should amuse yourselves in the following way.
I usually don't do them until like before the exam. Yeah. It's for the midterm I did when I was younger. Well, some of them I skipped. It's like job and joy and extraction and like 16.
I didn't even do the ones leading up to them. Oh, I know what you did. I looked at my ones. These are hard. I don't want to depress them. I don't know if they're useful or
Just do only those parts. Now, I want to talk about the reaction of nucleophiles onto carbonyl groups. I've mentioned this before because if you take a Grignard reagent and you add it to a carbonyl compound, you know that it adds to the carbonyl carbon. But I want to go back to that topic again for a reason that you will see in a moment. If you have a carbonyl compound, and you treat it with some sort of acidic substance, then one of the things that happens is that the oxygen becomes protonated in the way that I'm saying, that I'm showing. And you can understand, of course, that for the protonated species, I could write a resonance structure in which there is a plus charge on the carbon that was the carbonyl carbon. And so A minus is now obviously going to attack at that position. And so what you get is a species of that type. Now, many of these reactions in which you treat a carbonyl compound with some nucleophile that has got an acidic hydrogen, many of them are reversible, and that's why I've shown those arrows pointing both ways. Now, the next point I want to make is if you try reactions like that on aldehydes and ketones, you will notice a difference. And the difference that you'll notice is that the aldehyde is more reactive. Now the question then comes to your mind, why should it be that the aldehyde is more reactive than the ketone? And there are two factors. One is, as a nucleophile is attacking that position, as it gets close to the carbonyl, it's going to become aware of the bulk of this group and the bulk of that group. And likewise, as the nucleophile approaches this carbonyl carbon, it will become aware of the bulk of that group and the bulk of that group. And you know, excuse me, that hydrogen is much smaller than anything else. And so the steric accessibility in the case of the aldehyde is greater. So that's one factor. But there is another factor that's a bit more subtle. You know that alkyl groups are electron donating. And a moment ago I showed you that there you can write a resonance structure with a plus on the carbonyl carbon. Now if you have two electron donating groups on that carbon, as you do in the case of a ketone, clearly the size of that plus charge is lowered because the alkyl groups shove electron density towards that positively charged carbon. So the size of that plus charge is less. In the case of the aldehyde, you've got only one alkyl group pushing electron density onto the positively charged carbon. So the size of the plus group is not diminished so much. So guess which one has the biggest plus charge on it? Obviously the aldehyde. So for both steric and electronic reasons, aldehydes are more reactive. And it's all very understandable in terms of those two factors. Now, having told you this, I'm now going to tell you about a rather important reaction of aldehydes and ketones when you put them into an alcoholic solvent like ethanol or methanol, and you add an acid catalyst. This is a reaction that's very often done, and it's very useful. I'll tell you in a moment why it's useful. But first of all, I want to tell you what the reaction is, and I want to explain to you how it works. I just had a quick look at what's in the book, not because I don't know what's in the book, but I wanted to find out whether the book did aldehydes or ketones first. The book does aldehydes first, so I'll give aldehydes. I hope you believe me that I know what's in the book.
No, they have. Look at it. Today. Oh, really? There's so much here. If you see our comments. Oh, we don't have to do too much.
That's the whole reaction. This is called an acetal, and this one is called a hemiacetal. Hemiacetal. Hemi just means half. And you can see what has happened in this process. I haven't told you the mechanism yet, but this sp2 hybridized carbon has been changed to sp3. And instead of having a carbonyl group, you now have a sort of double ether. You see, this is an ether, and that's an ether, and it's a geminal ether, because they're on the same carbon. And these things now are not carbonyl compounds. Now, you know something about ethers. You can infer something about ethers. They're pretty stable compounds. You can make a Grignard reagent in diethyl ether. But you can't make a Grignard reagent in a ketone solvent, like in acetone, because if you generated any of the Grignard reagent, it would react with carbonyl. So supposing you have a carbonyl group in your molecule, and you want to use a Grignard reagent to do something else, somewhere else in the molecule, clearly you have to protect the carbonyl group while you do the Grignard reagent, and then later on, you have to regenerate the carbonyl group because perhaps you want it. And this formation of acetals is one of the best ways of protecting the carbonyl group. And you'll notice that all these arrows are reversible. All these steps are reversible. That immediately tells you that once you've made the acetal and done some chemistry over here that is incompatible with the presence of a carbonyl, you can then reverse the formation of the acetal and regenerate the carbonyl. But of course this bit is now changed because you've done some chemistry there, done some reactions that are not compatible with the presence of a carbonyl. So this is why this acetal formation is so important. It is used as a method of protecting carbonyl groups temporarily. Now there are a few other things I need to tell you. These heavy acetals are usually unstable. But there is one type that you can actually put in a bottle. And that type is this. Now, let me refer back to the last lecture or the lecture before that. I told you that esters are reduced by diol down to the aldehyde level. And this is a cyclic ester, so it's reduced to this compound, which is in equilibrium with the aldehyde. And for most of these lactol examples, the equilibrium lies well over on the side of the lactol. And so this is a special type of hemiacetal that's reasonably stable. And there's another type of hemiacetal that's a lot more stable, and that is this one. Now, if any of you are feeling tired and looking at the clock, oh my God, I've got another 20 minutes of this heavy-duty science stuff, you should just eat some of that. Because it's glucose. And it will feed your brain pretty quickly.
That was very loud.
Now you can see that this is a cyclic compound with oxygen in the ring. This carbon is attached to that oxygen, it's also attached to an OH. So it's exactly the same as this, so it is a lactol. And of course it is in equilibrium with the open form. In other words, this bond comes here and this comes out. And I've used a notation that you haven't seen before. I've got this squiggly line. And what does that mean? That means that some of this compound has the OH down, and some of it has the OH up. It's actually a mixture. So there are a few hemiacetals, special ones, that are lactols, that you can isolate fairly easily. But in general, these hemiacetals are not stable. Now for the same reason, well not for the same reason, but along the same lines that a hemiacetal is not stable, you will find that if you take an aldehyde and you put it in water with a trace of acid, you will get, by the same mechanism, this compound. It's exactly the same. Instead of alcohol, I've just got water. But these things are very unstable. And in order to be able to isolate them, this group has to have certain properties. And the property it has to have is that it must be very, very strongly electron withdrawing. And the common example is this. You can actually isolate this compound where you have 3 chlorine atoms on the carbon that's attached to the aldehyde carbon. But apart from that, it's got a special name. It's called chloral hydrate. I think in the old time movies, if gangsters wanted to make somebody unconscious and they were in a bar, they'd put a little bit of that chloral hydrate in the other fella's drink. And he'd drink it off to show how tough it was. The next one was just flames back out cold. Don't try this experiment. Did somebody say why not? Because it's illegal. That's why not. Dangerous. Oh my God. Okay. What I've told you so far is what happens if you take an aldehyde and treat it with an alcohol in the presence of an acid catalyst, you get, first of all, the hemiacetal, and then if you allow the reaction to go on further, you then get the acetal, and I've told you that all those reactions are reversible, and I've told you that forming the acetal is a way of protecting the carbonyl group. The other thing that I told you is that if you do a similar reaction with water instead of an alcohol, you'll get a hydrate. The hydrates are very, very unstable, and only in special cases can you isolate them. I've also told you that a few hemiacetals, those derived from lactones, give an isolable hemiacetal, which is given a name. It's called a lactol, or in this special case, it's glucose. So I told you those things. What I need to tell you now is two other things. I use an aldehyde as an example. Absolutely everything that I've said about forming a hemiacetal and then an acetal, and the fact that the reactions are reversible, also applies to ketones. But I'm not going to go through and draw it all again with an alkyl group there instead of hydrogen, because you get an alkyl group there, and I'm not going to do that. But what I am going to do is to use the example of a ketone and show you how to go backwards. In other words, how to hydrolyze the acetal, or the ketal as it's called in the ketone, and regenerate the carbonyl compound. Now, if you follow all that, you can see that I start off with acid, and I end up with acid. So it's acid catalyzed. And because all the steps are in equilibrium, they're all reversible, if I use a lot of water, that will drive the equilibrium over to the right. And so eventually I end up with the ketone. So if you have a ketal or an acetal, so this thing here, because it's derived from a ketone, is called a ketal in many books. If you take a ketal or an acetal, and some people use those terms interchangeably, irrespective of whether you're dealing with a derivative from an aldehyde or a ketone. If you take a ketal or an acetal, put it into water, and a little drop of acid, stir it around or heat it, what happens is that you get the carbonyl compound because the ketal or acetal is hydrolyzed by the mechanism that I've given you. There's one little twist to this, and that is that you can make cyclic ketals. And the way that you make a cyclic ketal is simply to take a ketone and use an alcohol that has two OH groups on it. And everything is exactly the same as the mechanism that I gave you with ethanol. Except instead of a second molecule of ethanol being required to generate the acetal or to generate the ketal, once the first molecule of that diol has gone in, it already has a second OH group that's ready to come down and cyclize. And so you can get cyclic ketals, they're very easy to make. They're a little bit harder to hydrolyze, and you can understand why they're harder to hydrolyze, because once you kick one of them out, it's held quite close to this carbon, so it likes to come back again. So it's a more effectively, it's able to compete more effectively with water than if, once you've kicked one of these out, it drifts away. So that's the reason why these are generally more stable. Now, I started all this business of ketals and acetals by first writing down a generic structure of a ketone and saying if you treat it with an acid HA, then the carbonyl oxygen is protonated. And I wrote down a resonance structure that showed a plus charge on the carbon, and then I drew for you A minus attacking that, what was that carbonyl carbon. That's what I did. And then I went on to this stuff, where the nucleophile is an alcohol. In most of the examples, it was ethanol. But it could be methanol, it could be this diol, which is called ethylene glycol. It's the stuff you put in the radiator of cars, it lowers the freezing point of the water. So the nucleophile in all these cases was an oxygen nucleophile. Now I want to tell you about nitrogen nucleophiles. Now, this business of nitrogen nucleophiles is actually rather important because inside your eyes, there is a substance with some double bonds in it that is linked to some protein by the type of compound that I'm going to describe in the reaction between carbonyl compounds and nitrogen compounds. It's a very important compound that's inside your eyes. And when you see somebody that's fancy, the first thing that happens, the very first thing that happens is that one of the double bonds inside this substance in your eyes changes from Z to E, or E to Z. I forget which way around it is. That's the first thing that happens. I'll now tell you about this so you can understand what's going on. There's some other things that happen if you see somebody fancy. The diameter of your pupil increases. It's a very subtle thing. And the chemical that was first used by Italian women, they're going out on a date, they put some of this stuff in their eyes because it makes the pupil of the eye bigger. And then any gentleman that they met would think, wow, this lady's really interested in me. They wouldn't, It's very, very subtle. We're not aware of this, but it actually happens, and that's what's going on. But that's another story. The compound that's put in the eyes to do that, used by Renaissance Italian women, is called atropia belladonna. And belladonna means beautiful girl. And so you can see the relationship between that name and its effect. Okay, so what happens if you treat a carbonyl compound with a nitrogen compound? The substance is called an imine. So in your eye, you can imagine you've got an aldehyde, and on the protein you've got an amine, an NH2, and by imine formation these two bits are linked together. And when the double bond geometry in this changes, it changes the shape of this, it sends a message to the brain. How does this imine form? Well, the formation of the imine is frequently, but not always, acid catalyzed. And so you can imagine that the oxygen is protonated to a small extent. Now, the carbonyl oxygen is much, much less basic than the nitrogen of the amine. This thing is called an amine. I know we haven't done amines yet, but that's what it's called. So you only need a catalytic amount of the acid. So some of the nitrogen is protonated and it can't react. A little bit of the carbonyl is protonated, and then it becomes much more reactive. Sometimes you don't need acid catalysis. So you can see that that mechanism follows pretty closely on what you would expect from the generic example that I gave at the beginning of the lecture, in which I used HA as the nucleotide. Now, there's something I can tell you about these imines, and this group R, let's number them. This group R and that one can be on the same side, or they can be on opposite sides. So you can get two isomers, because, let's do this. A and B. See, isomer A is different from isomer B. The shape's different. In this case, the methyl and methyl group are on the same side, and in this case, the methyl and methyl group are on opposite sides. So these imines can exist as geometrical isomers. Now, in the past, I suspect the only examples of geometrical isomers that you come across have been simple carbon-carbon double bond compounds, where you could get Z and E isomers. But you could also get Z and E isomers. And the shape of these molecules is that they're flat. So it's just like a double bond compound, except except instead of one of the carbons, you've got a nitrogen. And on that nitrogen, you have only a single substituent. Now the next point to make is these nitrogen compounds, these so-called amines, which behave as nucleophiles towards aldehyde carbonyls and ketone carbonyls. The next question is, are those the only nitrogen nucleophiles that do that? And I suppose you would wish that they are, because then there's less for you to learn. But unfortunately, they're not. There are a few other nitrogen compounds that you need to know about, and I think I've got enough time to tell you about them, so that you have more to study over the long weekend. If you don't have anything else to do, you can study just chemistry all the time. You'll probably be so happy you'll sort of die and go to heaven.
Obviously, that's what's going to happen.
Better, or we just have to. That's true. That's gonna be like all the way. Yeah, it's like okay. He says certain words are like what? Okay, he has one.
I've been to his office. Someone sold him a Bendy.
Oh.
It was like hanging there. He was like, yeah, 1 year. Like, it was just slipped under his door. And
Yes, yeah, and a fire. That wasn't kind of.
yeah.
It's the last time. So I don't have school tomorrow. And you're supposed to.
So this is another nitrogen compound. The reagent is called hydroxylamine. It's a hydroxyl group on ammonia, hydroxylamine, and the product that's formed is called an oxy. The other reagent is hydrazine, and the compound that it forms is a hydrazone. And the mechanism is exactly the same as the one that I wrote down for a simple amine. They're acid catalyzed. There's a very famous hydrazone, it's this one, 2,4-dinitrophenyl hydrazone. If you are interviewing somebody for a job as a chemist, as an experimental chemist, and you want to find out if they're any good, what you can do is you can give them a spotlessly clean lab coat, have a look at their hands, and ask them to make 2,4-dinitrophenyl hydrazone. And then when they've made it, you look at their lab coat and you look at their hands, because these things are very highly colored, and unless you're pretty good, you're going to get colour all over your hands. So if the person presents a bunch of sort of orangey red paws in front of you, you know that they can't keep it down in the front. Okay, I think we're ready for the one we think.